Hello, everyone. You are welcome once again to today's lesson. And in today's lesson, we are going to continue from where we left off in the lesson on calculus, specifically differentiation. Okay, so today's lesson will be lesson 3. In our previous lesson, we looked at what the various rules, okay, that you need to differentiate what functions. We did the power rule, we did the constant power rule, okay, we did the sum and difference rule, okay, and the differential of a constant rule. Okay, today we'll be looking at how best to apply the rules that I just mentioned, especially the quotient rule and the product rule. Okay, then after that, we'll look at another rule, the last rule that I showed. Okay, then, okay, we'll look at general questions. So quickly, let's look at, okay, this particular question. So we are asked to differentiate the following functions, again, with respect to what x. So we know we are dealing with d, dx of the functions that we have there. But the function didn't come with any names. Don't worry, your function must not necessarily be named. What you have to know is that you have a function to differentiate. That's all. Okay, remember I told you in our previous meeting that anytime in the question you can avoid the product rule, the quotient rule, you avoid. And subsequently, the power rule. In a situation where you cannot avoid, that's where you restrict yourself. It means the question indirectly is restricting you to use that particular rule, be it the power rule, the product rule, the quotient rule. So we said for the quotient rule, for you to avoid, the denominator should be a monomial and containing your variable. Okay, however, if you look at the functions that we have here, the denominators are not monomial. So but you can see quotient, a function being divided by a function. Obviously, we cannot avoid the quotient rule. So let's look at how best to deal with it. I'll pick one or two questions because we have calculus is very broad. Okay, so question number 6A. Okay, what are we giving? We are giving 2x plus 1 all over 3x minus 2. And what are we supposed to find? We are supposed to differentiate with respect to x. So it means we need to find d dx of what? Of both sides. I mean, of the function that we have here. So in this case, I'm going to write but d dx of my function here, which is 2x plus 1 all over 3x minus 1 will be equal to. So my operator, my differential operator is affecting quotient of what? Of functions. So here, what do I do? Let me calm down because of, okay, the rule involving the quotient. It will need more space. So if you have space, you will continue, but I realize that it won't go there. So that's why I'm coming down. Okay, so this will be equal to, remember the rule, we said hold the denominator function. So the denominator function is a binomial, put it in brackets when held, 3x minus 1. Then differentiate the numerator function. So you find d dx.
This
okay.
is minus 2.
It's minus 2. Okay. So at this point, I'm solving my own questions. Okay, so then d dx of my numerator function, which is 2s plus 1. But that's not all. Minus, I swap. This time around, I come and hold my numerator function, which is a binomial, so I have to put it in brackets. Then differentiate my denominator function. So d dx of my denominator function, which is the 3x minus 2. But that is not all. The whole of this over the denominator function squared. So the denominator function is 3x minus 2 all squared. Is my point well made?
Yes,
okay.
please.
As you mature, okay, you can skip this particular step where you need to differentiate the function straight away. So in this case, I'm going to get, this will be equal to, I hold my 3x minus 2, differentiate this, and I can see that my operator is affecting sum of two functions, so I have to differentiate term by term. So if I differentiate 2x, I will get what? 2. If I differentiate 1, I will get what? 0. So the differential of a constant is, so it means the differential of this function here will give me 2. Now I come to this one minus, I held what? 2x minus what? 1 or plus 1, sorry. Okay, then, okay, I'm going to differentiate this function with respect to x. So that will also give me, if I differentiate it term by term, difference. So if I differentiate this term, I will get 3. Then this will give me 0. So it means 3 will be here. But that's not all over my denominator, which is what? 3x minus 2, the whole of that square. Is my point well made, my professors? Okay,
Yes.
so at this point, the denominator never expand, because if you have any algebraic fraction, if you can reduce, then the expression, numerator denominator expression must be in the factorized form before you can clearly see that, okay, your expression, rational expression for that matter, can be, okay, simplified. So the denominator is already factorized, so don't touch it. So leave it like that. So I'm writing that one first. It needs no, okay, or letter work. So now what do we have? You come and expand the numerator and combine items, if any, and factorize to check if you can reduce. So in this case, if you expand, we are going to get 6x minus 4. If you expand this, we are going to get what? Minus 6x, okay, minus 3. Do you agree? Okay, so in effect, we are going to get, okay, minus 6x plus 6x. Okay, so that will go. So I'll get minus 4 minus 3. So that will give me minus 7 sitting in the numerator all over, okay, my 3x minus 2, okay, squared. Okay, so if you want to be smart, instead of writing the but, you can write therefore there. Okay, then in that case, you don't draw your conclusion. So that is what I am equally going to do there. Okay, so I will erase this, then put therefore there. Okay, as simple as that. Point well made. We'll solve one more question, then after that, okay, the rest of the questions maybe you will try. Okay, all right. So this is what we have. Okay, so now let's go and look at what the, which other questions should we pick? Okay, I want us to go for, okay, this particular one. Or let me go for the D. If you're able to do D, then with these two, okay, these two that you have, the E and F, because of their special power or powers, okay, you cannot do it until you know the power rule, or what we call the change rule, the composite function rule. Okay, remember I told you a power rule. Okay, that one is, but usually from the basic rules, okay, usually for me, I consider the power rule to be the composite function nature. Okay, but in actual fact, the power rule is the basic rule where you have a function to a certain power. Okay, so my point is the last two, this and this, you cannot use the quotient rule without applying the power rule. Okay, or did I say the power, the composite function or the chain rule? Okay, so now, D, what are we giving? We've been given x cubed plus what? 3x squared plus 2x all over, okay, s squared plus what? X. Okay, so now you should know, therefore, I am going to differentiate. So the function didn't come with a name. I'm not bothered because I'm asked to differentiate with respect to x, which means I need to find dx of the given function, which will be your x squared, okay, plus 3x squared plus 2x all over x squared plus x. Okay, in some books, you see this put in bracket. But for me, every fraction, that's a single fraction. Okay, anytime I'm applying anything on it, I don't put it in bracket because it's usually not necessary. So in this case, I'll write that is equal to, I'll come down. What I'm going to write, I know it won't go there. So I will hold my denominator function, which is x squared plus x. It's a binomial. Don't forget to put it in brackets. Other than that, okay, you'll be in a very big trouble. So then you go and differentiate the numerator. Okay, so in this case, I am differentiating the numerator straight away, but I will advise, I am doing this, going to write this. Okay, so if possible, write it as a guide. Okay, I think let me rather deal with it the matured way so that you can also appreciate the matured way. At least I've done this one, so that's okay for you to appreciate. So let me look at it from the matured perspective. Okay, so now hold the denominator, differentiate the numerator function terms. So I'm going to differentiate. If I differentiate term-wise, I'm going to get 2x plus what? 6x. Is it cube? No, this one is cube because you cannot have 2. So this will give you, let me go and do the right thing. You can't have 2x terms in the same question. So let me do the needful. So that will rather give us, okay, 3x squared. Okay, then plus 6x, then plus 2. Okay, minus, now you come and hold the numerator function, which is what? Your x cubed, x cubed plus 3x squared, okay, plus 2x. Okay, then what else? You differentiate the denominator function, which if you differentiate, you get 2x, okay, plus 1. All correct. All over your denominator function squared, so x squared plus x all squared. Is that clear?
Yes, please.
Okay, so at this point, you expand both, the numerator, combine like terms, then you simplify, if possible. Okay, so I guess I can leave you here for you to continue, okay, later. So you distribute this one times the whole of this one times the whole of this. Then this one too, okay, it will be minus, okay, this times the whole of this, minus this times the whole of that. Okay, so take note, or you can push the negative through. In that case, each one will be negative, negative here. Then this becomes plus. Then when you add this to be this one times this one times this, 2x will multiply all the negative terms here, provided you push the negative inside. And the 1 will multiply all the negative terms here. Or if you like, you can keep this one to be positive and multiply the negative by this. So negative 2x minus 1, in that case, minus 2x will multiply all that you have there, minus 1 will multiply. You end up getting the same result. Can I move on? Please, can I move on?
Yes, please.
Okay, so once you appreciate that, let me move on to, okay, the chain rule. But before that, there was a question that I wanted to, I think I skipped. I should have started from, yeah. Okay, so let me start from here. Okay, let me start from this question. I think I would have addressed that situation. Okay, so this is it. In this particular set of questions, you can see you have power. Anytime you have power, I've told you if you can avoid the power rule, avoid. Okay, the composite function, anytime you see a function which is not x but x, okay, any function which is not x to a certain power. Okay, please take note. This one is x plus a certain or minus a certain quantity. So you need to use the power rule. However, remember, we can use the product rule as well. So see this one as x minus 2 multiplying x minus 2, and you use the product rule. Or, like I said, avoid. So anytime you can expand the given function, expand and differentiate term by term. So you can avoid, okay, all the rules. Product, okay, obviously quotient will not be here in the power. This one too. So my advice is, if the power is 3, okay, expand, because we all know how to expand based on binomial theorem, any function to the third power. Okay, it's to the power 4 that usually it will be, but to the power 3, you should be able to expand. So you can avoid, okay, the product rule or the power rule here. And equally, you can avoid the product rule because you can expand and differentiate term by term. You can equally expand this and differentiate term by term. By that, you have to expand this, which gives you s squared plus 2s plus 1. Then you come and multiply it by all the terms here. Remove all the bracket, then after that, you differentiate term by term. Now, if you come to this one, to remember this is a situation that I said, if the denominator, you have quotients, all right, but once the denominator contains a monomial, which contains your variable x, then you should know you can avoid the quotient rule. So let me quickly take you through that E and see the technique. So what am I giving? Y is equal to x to the power 5 minus 3x squared all over x. I can avoid because I know that this is the same as x to the power 5 over x, which will give me s to the power 4. Then minus 3s squared over x, which will give you minus 3x. Do you agree?
Starting this is x cubed.
It's s cubed. Oh, okay, s cubed. Thank you. So it means s squared. Okay, so at this point, dy dx. So I can write therefore dy dx. Okay, will be equal to, I will differentiate term by term. So that will give me 4x cubed. Okay, minus 6 what? X. Okay, that you have there. As simple as that. Okay, however, imagine if you were supposed to use the quotient rule. You hold this, come and differentiate that. Before you even write the rule itself, we will be done with our answer. You get the point?
Yes, please.
So if you can avoid, you avoid. So all the quotient that you see here, you can avoid. And with this one too, you see product in the numerator, then this. So what you are supposed to do is, so let me deal with h. Okay, y is equal to 3x minus 1 into what? X plus 4 all over, okay, 2x squared. So when I have this, I have to go and expand my numerator. So this will be equal to, so I want to avoid product rule, quotient rule. So if I expand, I will get 3s squared, okay, plus what? 12x, okay, minus x, then minus 4, all over your 2x squared. So on that note, we are going to get 3s squared, only one term in s squared. This can be combined, plus 11x, then minus 4, all over your 2x squared. But because you have a monomial, you can divide, okay, each term so that you avoid the quotient rule. So on that note, you are going to get, okay, 3x squared over 2, is it s squared? Yep, I think it's s squared. So over 2x squared, then plus 11x over 2x squared, then minus 4 over 2x squared. So in effect, we are going to get what we have here. The s squared will cancel, so we get 3 on 2 here. Then what? Plus, this will give you 11 on 2x. So 11 on 2, okay, x. And the other one will give us, okay, 2 over s squared. Do you agree?
Yes, please.
Okay, so remember, again, after your purpose, your intention was to avoid the quotient rule. After dividing, you can see x also in the denominator. But remember, each of them is just a term. So you take it up. Okay, so this becomes 3 over 2, then plus 11 over 2, then your x goes up, the exponent becomes negative. Then minus 2, the x goes up, the exponent becomes negative. Then now you differentiate term by term. So at this point, you can see that I've not written dy dx, so I have not differentiated yet. I'm only working on my function for me to avoid using the quotient rule and therefore the product rule. So on that note, I am going to get, okay, dy, therefore, okay, dy dx will be equal to, if I will differentiate term by term. This one, if I differentiate a constant, it will give me 0. This one, I need to bring the negative 2 down. So I'm going to get negative 2, okay, times, okay, 11. Okay, we are mature, so let's do that mentally. Okay, so once we are matured, that can be done. However, if you know you can't do it mentally, do it systematically. Okay, so, oops, what happened? Okay, I've cleared what I'm not supposed to clear. Okay, all right. So I think this is over n plus 11x over. Okay, so now this will come, that the negative 2 will come and multiply the 11, but the negative 2 and the 2 the 2 will cancel. So I'll get -2, the 2 and the 2 in the numerator. So I'll get what? 2 will cancel, so I'll get -11 x to the power -3. Okay, then minus, this one will come down and multiply, so I'll get plus. So I'm going to get what? 4 x to the power -3. Hey, this one, is it x to the power -2? It's x to the power -1. You didn't prompt me. Okay, so if that's the case, then this changes. Okay, so what you have here will change. It's -1 because you brought this one up, and the exponent of the x in the denominator is 1. So take note. So -1. So in this case, this gives you -11/2. Okay, rather. Then this one will give you plus. Okay, so this one becomes -2 instead. Then this one will be -3. Okay, so at this point, remember, the question didn't come with negative exponents. So I am going to rearrange. But remember, I told you, if you have a negative term, an expression, and there is one positive term, start with that positive term. Don't start with a negative. So I'm going to start this time around with this. So I will get 4. My s goes down, the exponent becomes positive. Then -11/2, my s comes down, and the exponent becomes positive. Is that clear?
Yes, sir.
Okay, great. Okay, so that will be it for this set of questions. And with this one too, you can equally avoid, okay, the quotient or whatever. So expand. Okay, this one to expand and divide each of the terms. So now let me move on to, okay, so same for this one. Product rule. Okay, ordinarily you are supposed to use the product rule. But just as you can see, we can avoid, we can expand this easily, then avoid the product rule. Okay, so that you differentiate term by term. This one to quotient with the denominator not being what? A monomial containing x. So you have to, you cannot avoid the quotient rule. Take note. Okay, and we've done a question more difficult than this, so you should be able to do this. Okay, so that was just by the way. You have to go back. Okay. So now to what we call the chain rule. Okay, the chain rule or the composite function rule. Okay, so here, anytime you recognize that you are dealing with what? A function that is a composite function. And how do I recognize a composite function? We've all done composite functions. So when you can see that your resultant function, okay, can come or is as a result of applying 2 or more functions successively, then you should know that you are dealing with a composite function. But usually for me, this is the trick. Anytime you see a function of this sort, then it requires the chain rule or the composite function rule. Anytime you see your function, let's say I have a function f of x, okay, to a particular power, maybe n, any function. And the chain rule or the composite function rule, okay, is the general rule for all differentiation. Okay, so all the other rules, especially the one that the power rule takes its source from this. That's the more reason why usually I call this the power rule, because that's the main power rule. So if I have any function, remember, if you have any function and you have the function to a power, okay, this is all that you need to do if you want to differentiate. So if I have this, then d dx, I'm differentiating this function with respect to x because the function depends on x, of f of x all to the power n. Okay, this will be equal to, this is what you do. You know, anytime you are differentiating any function to a certain power, what do? You bring the power down. Is that not it? If you have x to the power n, we said this will differentiate into n, break the n down, your x, reduce the exponent by 1. Is that not it? Hello,
Yes,
are you with
please.
me? So it's the same thing. My differential operator is affecting a function to a certain power. So I bring the power down, then keep my function. So my function here is f of x. Okay, But what do? I subtract 1 from the exponent, so it will be n minus 1. Is that clear? But unfortunately, that is not all. It is supposed to be times the differential of the function itself that you are raising to the power. So it will be d dx of what? F of x. So this is the composite function rule or the chain rule. This is taking its source from that. Because if I have, see, if y is equal to s to the power n, so forgive me, and I find dy dx, okay, it means I'm finding d dx of x to the power n. And per the composite function rule, okay, we said bring the exponent down. So this is a special situation of this. Bring the exponent down. So this will be equal to, bring the exponent down, which will be n. Keep your x, reduce the exponent by 1. But that's not all. It will be times d dx, okay, of your function that you are raising to the power, in this case, x. But because we know that if this is x and you are differentiating with respect to x, this quantity will always be 1. So when we are quoting the rule, we don't attach this because this will always be 1. So we end here. However, in certain situations, your function that you have in brackets, okay, its differential will not give you 1. So it means you need to attach, okay, this factor that you have there. So assuming maybe I give you 2x minus 1 all to the power 3. Okay, now this is the function that I'm raising to the power. So if I'm differentiating, I'll bring this one down. Okay, keep my function, reduce the exponent by 1. Okay, but unfortunately, I cannot end it because what I have in bracket that I'm raising to the power, okay, its differential will not give me 1 for me not to consider it. With this one, I've told you if it is x, just x. Okay, with a linear with your constant, your a being 1 and your b being what? 0. You have that. You should also always know that the factor that when you differentiate the function that you have here to the power, okay, that will give you 1. So you usually don't consider it a special situation. So all the differentiations, okay, you need to know the composite function because that's especially where you have powers. That's where, okay, the rule becomes very useful. That's where the foundation is taken from. So let's see how best we can apply, okay, the concept that we have there. So let's look at the following questions and the solution. So we are supposed to find dy dx of the following. So it means the operator here is d dx. So we are differentiating each of the functions here with respect to x. So A, solution to, so A, no major question number. Okay, what am I giving? Y is equal to 2x plus 3 or q. Okay, like I said, you can avoid, especially when it is q. Only that some teachers also advise, usually advise that when it is squared, okay, but beyond squared. But I know you are matured now to expand, okay, the power 3 easily. However, if you can't, then the power rule becomes the efficient way. So in this case, I'll write, okay, this implies that I'm taking dy, d dx on both sides. So I'll get d dx of y, then that will give me dy dx, and that will be equal to d dx of my function that is here. And that is what? 2x plus 3, okay, q. But the function that my operator is affecting is a function to a particular power. So I will use the power rule or the chain rule or the composite function rule. Okay, so I will write, okay, this is equal to, okay, now what do I do? Per the rule, bring the exponent down, so 3 will come down. Keep your function that is raised to the power. Reduce the power by 1, so that will give you 2. But that is not all. Times what? The differential of what you have here. Let me write it, d dx of the function in bracket, and that will give you 2x plus 3. That's the function in bracket to the power. So in effect, I'm going to get therefore my dy dx will be equal to 3 into 2x plus 2, or sorry, plus 3 squared. Then if I differentiate this, that gives me 2. Do you agree? Okay, so normal differentiation, power down, keep your, okay, function that you are raising to the power, reduce the power by 1. okay, then times the differential of the function that is raised to the power. So here we can end here, obviously, because we can easily multiply this. So that will give us 6 into 2x plus 3 all squared. So this becomes the differentiation. Okay, if you expand and differentiate 10 by 10, you end up getting only that if you expand and you differentiate 10 by 10, your results will not be in the factorized form. The nature of the function came in the factorized form. So you will factorize your results and you end up getting exactly what you have. Is my point well made? We'll do maybe 1 or 2 more. Okay. Okay. In this situation, you can expand, but especially when the exponent is 1, I mean negative, and maybe a fraction. Remember, binomial expansion, okay, you cannot get all the terms. Therefore, you can't differentiate 10 by 10 if you expand. So in that case, when you see the exponent to be negative, to be a fraction, you should know that you are restricting you to the use of what? The composite function rule or the chain rule. Okay, so at this point, what do we have? The next one, I'm going to ask for the power, positive power. We know this one, expanding will be difficult. Okay, a little involving. So what do? I will use the power rule. I will bring the 5 down, keep this, reduce the exponent by 1, but that's not all, into bracket times what the differential of this, which will give me 2. Then I go and deal with it. Now let's go and look at the exponent, the negative exponent. Okay, then we'll take one of the fraction exponents. So C, what are we giving? Y is equal to 5x squared minus 1 all to the power negative 3. So what do we do? Pair, all right, therefore, dy dx will be equal to, remember the rule, bring the exponent down, minus 3 will come down. Keep what we have there, so 5x squared minus 1. Reduce the exponent by 1, minus 4. But that's not all, times the differential of what you have in brackets. And we are going to do that mentally. So times what? 10, what x? Is that clear? Is my point well made, or I should come again?
It's well made, sir.
It's well made. Okay, so at this point, okay, check the factors that you can easily multiply and multiply. So you don't end there. This will be equal to, I can easily multiply the minus 3 factor and the 10x factor. So that will give me minus 30x then into 5x squared minus 1 all to the power negative 4. And here I can conclude with a negative because the question itself gave me a negative exponent. Point well made.
Yes, please.
Okay, so we are going to do one of the fractions. So I'll go for F. Okay, or let me even go for Y. Then so that E. Then F, I will just talk a little. Just one step involved. So E. E, what are we giving? Y is equal to, okay, 2x plus 3 all to the power half. The same technique. Okay, I'm differentiating therefore dy dx. Okay, will be equal to, bring the exponent down, 1 over 2, keep whatever that we have there, 2x plus 3. Then what do? Reduce the exponent by 1. So that will give us minus half. All correct? Okay, but yes, that's not all. Unfortunately, that's not all, times the differential of what you have in bracket, which will give us 2. You can choose not to put it in bracket. So now you can see that this 2 will cancel the 2 here. Is that clear? So in effect, we are going to get 2x plus 3 all to the power negative half. Okay, but like I said, if the question didn't come with a negative exponent, you can avoid. So you can write this one as 1 over 2x plus 3, okay, to the power half, or root of that. That's the matured way. So this question that we have here is basically the same as this. So here, after writing your y is equal to root of 2x plus 3, you know in differentiation, your exponent must be explicit. So this one will give you 2x plus 3 all to the power half. So it's the same question put in a different form. So you continue from here. All correct?
Yes, please.
Okay, all right. We can equally, just like binomial theory, we can equally give you, okay, 1 or over maybe root of a certain quantity, 2x minus 4. So you know that is the same as 2x minus 4 all to the power minus half. The exponent must be explicit before you start dealing with it. All correct. Then you differentiate, transform it to have an explicit exponent, then you differentiate. Okay, so that will be it for this particular one. Now, differentiation of implicit function. So far, you realize that all the functions that we have differentiated, you were seeing y is equal to, so y was explicit. So y is equal to x. Y is equal to x squared plus whatever, any constant. But please take note, it is not always that you'll be giving functions of that nature. Okay, you could be giving functions that y is not directly made a subject. So in that case, what do? And whenever you encounter that situation, you have to make use of what the technique in differentiating what implicit functions. So explicit, we know how to deal with that. And we are going to look at what implicit. Take note, we know anytime you have d dx of x to the power n, this will give you what? What will be your result? Anytime you are differentiating any function with a power, bring the power down. Okay, keep your function, reduce the power by 1, then times the differential of what? The function. But this will give you d dx of x. That will give you 1, so usually don't consider it. However, let's look at this. Assuming I have d dx of, okay, y, okay, to the power n. The same technique, bring the power down. Keep your y, reduce the exponent by 1. But unfortunately, this time around, okay, the quantity that is your d dx, okay, of your y will not give you 1. It will rather give you dy dx. Do you get it? Should I come again, my professors?
Please come again.
Okay, all right. So remember I told you that anytime you are differentiating any function and it is raised to the power, okay, we are supposed to use the composite function differentiation technique. Okay, the rule that I just walked you through. Okay, and the rule I said, anytime you have a function to any power, okay, I have a function, okay, to any power. The rule, if I differentiate this function, okay, I'm going to get what with respect to x. Okay, so I'm going to get, maybe, let me put it this way. Okay, raise the power. This is the rule. Bring the exponent down. Keep your function. Reduce the exponent by 1. But that's not all times the differential of the function itself. Is that clear? d dx, sorry, not dd. Okay, however, the other one, this one is also the same thing, only there is a special situation. So this is the same as times the differential d dx of the function to the power, and the function to the power is x. Do you get it? But d dx of x will give you 1. Dx will be dx over ds, that will cancel. Or even if you differentiate this function x, you know that it will give you 1. So the result here will be 1. So we usually don't consider. Okay, we'll end here because whatever you write here will not affect this value because it will be 1. You get it? So if you ignore, it will not be costly. All correct. Okay, so now again, I'm dealing with d dx of y, y to the power n. So I'm differentiating a function to a particular power. So that's the more reason why I always want you to, okay, write your operator. Fish out your operator, then attach your operator, and then ask yourself, your operator is affecting what kind of function? You can see that it's a function to a power. So it means I have to use the general power rule, which is the composite function. Bring the exponent down, keep your function that you are raising to the power. Your function down here is y. Reduce the exponent by 1, but that's not all times d dx of what? The function that is here to the power. And it will be d dx of y. But you know that this will give you n minus 1 to the power n minus 1. d dx of y will give you dy dx. You know this. Exactly. So it's the same technique. That's why you have the, if I have d dx, okay, of y, which gave you your dy, you know this is to the power 1. Okay, so this is, look at what is going to happen. I'm going to get, I bring the power down, 1 down, I will get y, 1 minus 0, which will give me 0. Is that clear? Sorry, 1 minus 1, forgive me, which will give me 0. Is that clear? I'm using the power rule. The power here is 1. So if you want me to write for you to understand it better, I'll write. Okay, I'm bringing the 1 down. So I'll bring the 1 down, keep my y, reduce the exponent by 1. So it will be 1 minus 1. But that's not all, times, okay, d dx of what? Of y. Okay, so in actual fact, what you have here will give you 1. Is that clear? Then it will be d dx of y, indirectly we know, will give us dy what? Dx, sort of. Okay, so take note. The point is, anytime you have d dx and it is y, it will give you dy dx. So if I have, assuming I have d dx, this time around, the exponent of the y is not 1, it is 2. Per the rule, this will give us 2 down. Keep your y, reduce the exponent by 1, so it will give you 2 minus 1, which is what? 1. Then it will be times d dx, okay, of what? Your y, which will always give you dy dx. So if you differentiate this, you get 2y dy dx. So anytime you are differentiating and the variable that you have here, it's not the same as the variable that you are differentiating with respect to. You always get, okay, the variable that is here, the variable that you are differentiating with respect to. So it means if I have, okay, d dz of y squared, this will give me 2y dy dz. Because I'll bring the exponent down, keep the y, reduce the exponent by 1, then it will be d dz of y, which will give you dy dz. Is that clear? Is my point well made? Okay, the implicit function technique is a little technical, but it's not difficult. Okay, so let's go and apply. Okay, this may be looking at examples, your understanding will be better. So we are supposed to find d dy dx of the following. So we need to know our operator, very critical. And the operator here is d dx. So here, obviously, you can see that your function y is not made a subject. So you are dealing with an implicit function. And for implicit function, you know the technique. So this is what we are going to do. So A, please take note. Your operator is very critical. So s squared minus y squared is equal to 14. So I'm taking d because I know my operator. My operator is d dx. So let me write an equation. So d dx of what? My left-hand side, s squared minus y squared, must be equal to d dx. It's an equation. Whatever I do on the left-hand side, I have to do same on the right-hand side. Do you agree? Hello, are you with me? As for implicit function, we'll do more. Yes, are you with me? Okay, so now you can see that your operator here is going to affect, okay, difference of function. So you have to use the differentiation of what? A difference of function rule. So I have to differentiate it 10 by 10. So it will be the differential of my first one, which will give me 2x. Do you agree? The variable that I'm differentiating with respect to is the same as this variable. So it means that factor times d dx of x will give me 1 after bringing the exponent down and doing it. So I will write it. Then minus, if I differentiate this, okay, this is the first example. So let me write the operator. Okay, one after the other, so that I don't have to rush. Okay, though we are behind time, the understanding is key. Okay, so what do we have? So this will be d dx. I'm differentiating term-wise of s squared minus d dx of y squared, okay, is equal to d dx of a constant you know is 0. Is that clear?
Yes, please.
Okay, so now you can see that the variable that is here is the same as the variable that you are differentiating with respect to. So in this case, that factor, which will be the d dx of what you have here to the power, the function to the power will give you 1. So if I differentiate that will give me 2x. Then here, the function, y, that the function that I have here, y, is not the same as the variable that I'm differentiating with respect to. The letter here is not the same as this. So it means if I differentiate, that term dy dx factor will be there. So I will minus 2y, then I will get dy dx. Is my point well made? Is equal to 0. Is that clear? Who wants me to come again? Remember, I told you it's a little technical. And I think last year also, implicit function came. So please take note. Okay, it's very likely, okay, it will come this year. Because looking at what students did, they couldn't, okay, deal with it squarely. So usually when that happens, it's likely they will repeat it. Most likely. So take note of this. So make sure you understand the differential of implicit function. So here, what were we asked to find? Dy dx. So you just come and make dy dx the subject. Okay, so my dy dx term is negative. I will move it to the side. Okay, then I will later go and divide. I always want to avoid negative from the initial stages or the initial stages. Okay, because I hate negative. So this indirectly, in my mind, I'm moving this one to the side, but I'll write it first. So I will get 2y dy dx is equal to, this will be maintained here, 2x. Do you agree? I write it again before I divide. I'm looking for dy dx. So I will divide by 2y. Okay, then it's equal to 2x, divide also by 2y. So this will cancel that. So I will get dy dx to be equal to, this will cancel that x over y. So therefore, dy dx is equal to x. Is my point well made?
Yes, please.
Okay, very good. Okay, so on that note, I'm going to skip, okay, this one here, okay, this one, and we'll go to this straight away. Then after that, maybe we come to this. Okay, so quickly, let's go and look at what the C, similar, okay, to what we just did. Okay, giving S cubed plus what Y cubed is equal to 9. So you are asked to find dy dx. So it means the operator is d dx. So I will take d dx of both sides. So this implies that d dx of the left-hand side, which is s cubed, I put it in bracket because it's more than a 10, is equal to d dx, okay, of 9. That's just a 10, so bracket is not necessary. So here, now I'm matured, so I'm going to skip this step. Okay, I will do it mentally. I'm going to differentiate term by term. So if I differentiate this, that will give me 3x squared. The variable here is the same as this, so that quantity times d dx of x will give you 1. Then plus, if I differentiate this, it will give me 3y squared, but that's not all because the variable here is not the same as the variable that I'm differentiating with respect to. So that will give me my dy dx, and it's equal to 0. All correct? Because d dx of what? Now, professors, are you following?
Yes, please.
Okay, great. Okay, so now what do we have? We are looking for dy dx. So pick it out. Thankfully here it is positive, so I'll maintain it here. So I'll get 3y squared, okay, dy dx will be equal to, I move this one, negative 3x squared. So you know what will happen. I write it again before I divide. So 3y squared over dy dx, okay, is equal to minus 3x squared over 3y squared over 3y squared. So this cancels that, and I'll get therefore dy dx will be equal to 3 will cancel the 3 here. So minus x squared over y squared. All correct. Points well made, my professors.
Sure.
Okay, so we'll be dealing with more complex questions. So this is question 1. As we move on, okay, I'll arrange my questions in some level of, okay, complexity. So now let's see the next set of questions. Okay, so look at this. Okay, question number 2. Okay, we are supposed to find dy dx of, okay, these functions. Okay, this time, unlike the other ones, you saw, let's go back and see. You saw that you only had what? A term. If your term is in x, it's in x. If it's in y, it's in y. You never had a term in both x and y. Okay, so here, look at what we have. you can see a term in X and Y terms. How do you deal with that? Don't worry at all. It's very easy. Once you know the product rule and you know the power rule or the composite function rule, you are good to go. So let's go and look at what the solution to question 2A. Okay, what are we giving? S squared plus xy, then minus 5 is equal to 0. Remember, okay, you are differentiating. So, but with respect to x, you should know your operator. Your function here is not an explicit function, implicit, because y is not made a subject. So you don't go and write dy dx of this. It is rather d dx, the operator of your function s squared plus xy, okay, minus 5 should be equal to d dx, okay, of what? 0. Someone can choose to move the 5 here, okay, then take d ds of what? The minus 5 here rather, and take d ds of 5 is the same thing. Okay, you still get 0 here, but I don't want to do that. I will differentiate straight away each side by applying the operator. Okay, so now I'm going to differentiate term by term. Okay, this time around, you know, this is what we are going to do. You get 2x. Do you agree? Do you agree? The differential of x squared will give us, okay, with respect to x will give us what? 2x.
Yes,
Are you with me? Okay, now you can see that you also have to come and differentiate this function. So we are going to have dds. Let me write it rather, because when you get it, then I skip. I usually want, okay, you to write it if possible. So I will get d dx of my first term s squared plus d dx of my second term xy, okay, minus d dx of my third term, which is what? 5. The minus is always, you can bring the sign, okay, of that. And that should be equal to d ds of this, which is 0. Okay, 0 is a constant. So if I differentiate, the variables are the same. So that will give me 2x. Now here, okay, xy. And sy means the product of x and y. Do you agree? So you will use the product rule in differentiating that. So by that, this is what I mean. Per the product rule, we said, hold the first function, so I will hold x. Then differentiate the second function. So times d dx of y. As you mature, I will skip some of the steps. But that is not all. Plus swap, come and hold your second function. Then differentiate what your first function. So d dx of x. Okay, then this we know will give us what? 0. So minus 0 is equal to that, but I won't write it. It's equal to 0 because I will get minus 0. Is that clear? Should I come again, my professors? Who wants me to come again? If you get the situation where there is a term in xy, you are good to go. Any function you should be able to differentiate, okay, implicitly. Can I move on? Are you all fine? So when you see xy, treat it as what? As a product. That's the point. All correct?
yes, sir.
Okay, so now I will keep this function, the operator is not affecting. So the x, I'm done differentiating it. Then the x will be there. The operator is affecting the y. So d dx of y will give us dy ds. Do you agree? Then plus y, d dx of x will give us 1. Is equal to 0. Is that clear?
Yes, sir.
So in effect, we are going to get 2x plus x dy dx, okay, plus y is equal to 0. What are we looking for? Dy dx. So maintain the term in dy dx here. So x dy dx. Then move the other terms to others. So you get, okay, minus 2x minus y. Okay, what do? You write it again and you divide. So in this case, I'm going to get, if I do that, I'll end up getting, therefore, my dy dx will be equal to what? Minus 2x minus y all over x. All correct? Is my point well made?
Yes, sir.
Okay, very good. Okay, so I will explain what we have here. Let me see whether the next set of questions will deal with what I have in mind. Okay, so with this one too, is the same concept. You treat this one as a product. Hold x, differentiate with respect to y. So I'll get differentiate y, not with respect to y. So x, so this will give you x dy dx plus y into 1. So it will be plus y. And this will give you 1 and plus dy. Okay, so this one will give us 2 terms in dy ds. Let's do that one so that you know exactly what to do. So d, okay, xy plus x plus y is equal to 1. Once I have 2 y terms, obviously, I will get, okay, I mean 2 terms involving y. Okay, I'm going to get 2 terms involving dy dx. So in this case, I'm going to get, this implies that d dx of this side, which is xy plus what? X plus y should be equal to d dx of 1. So let me see if someone is done. Okay, Kobe, I don't really get you. Oh, it was an old message. Okay, so the implicit function differentiation I've told you is a little technical. Okay, but the technicalities are more or less demystifying it. Okay, so not everyone understands. You mean here or in school? Here. Oh, really? So your spokesperson says not everyone understands. Please, you know, I've told you if you don't understand, okay, please let me know. If you keep quiet, I will assume you understand. You can say that that's my style of teaching. Every step on the way, I will ask you, are you okay? Because this is math. If you don't get it on that step, okay, going forward, you won't get it. That's the more easy. Every step on the way, I ask you, are you okay? What have you? So if you are not okay, let me know. And I've told you, very likely it will come. And it usually comes in the compulsory section. So make sure you get it once and for all. Okay, so that when you go back to school, your colleagues who really don't get it, you can explain to them. Okay, so now this is what we have. I'm going to differentiate these terms, but I will do it term-wise. So this is product of x and y. So I will use the product rule. So I keep x, differentiate the y with respect to x. So that will give me d dx of y, and that is dy dx. Okay, plus I will differentiate x with respect to, and that will give me 1. Then plus, I'll find d dx of y, which will give me dy dx. And that will be equal to d dx of 1, that is 0. So here I have 2 terms in dy dx. I will maintain these 2 terms and move this term to the side. So I will get x dy dx, okay, plus dy dx is equal to -1. Do you agree? So I factor out dy dx, okay, or in that case, usually we write it this way, but it's the same, x plus 1 in brackets dy dx. Or you can also write dy dx out, then x plus 1 is the same thing, multiplication is commutative. Then you divide through by what, x plus 1. Is that clear? Is my point well made?
So if you get the 1.
You can see that if you factor out dy dx, there will be 1 here. Okay, if you have, 1. You get it. If you have, okay, x squared, okay, plus x. If you factorize, what do you get? X will come out and you get x plus 1. Plus 1. You know, always what you get, you have in brackets here will be each of what? The terms that you have here. You divide by the factor that you took out. So this one, if you want to get the first term, it will be this one, okay, divided by dy dx, so you get x. This one divided by dy dx, and that will give you 1. That's the basic principle of what? Factorization. Is that clear?
Yes, please.
Okay, so now you write it again and you divide by, s plus 1. So it means, therefore, dy dx will be equal to minus 1 over s plus 1. Is that clear? All correct. Please, are we fine? I think I have to pause at this point, then ask you individually. Okay, so I have gone through. Kobe.
The answer is 2x y cube plus 3x squared y squared dy dx. Y cube plus 3x squared y squared dy dx.
3x squared
y squared
dy
dx.
dy dx. Very good. Okay, and this is coming from the fact that you treat this as product. So you hold your s squared, then find the differential of this, which will give you, okay, 3y squared dy dx. Do you agree that the differential of this will give us that? Okay, then remember, bring the power down, keep this reduced by 1, then times the differential of this. Then plus, you come and hold the y cube, then differentiate this, which will give you your 2x. So in effect, you are going to get what? If you multiply this, this gives you 3x squared y squared dy dx. Okay, which is his second term, but our first term, no worries. Then now you are going to get, this will give us 2xy cubed. Okay, so that will be the differential. So if you have this term anywhere in this expression, this will be its differential. That's all. Is that clear? So take notes. Okay, on this note, okay, I think I'm going to give you 4 minutes by 6, I think 20, we should all be back. Okay, and take note, I explained this. Okay, so you expand first, then you go back to your normal. Okay, and you differentiate using that technique. Take note of that. All right. So I think now I can pause. Okay, so welcome back from the water break. Now let's look at, okay, a situation, this situation, and how best to deal with it. It seems I didn't. Okay, assuming you've been given this to differentiate, okay, with respect to x, this is your function. So you have, okay, 2x plus y squared, okay, minus 3x squared y to the power 4, okay, plus 5. Or let me write is equal to minus 8x. You are asked to find dy dx. Okay, so let's do it together and see what will happen. You can see that so far, even the one with the product, the coefficient, okay, all along, either 1 or minus 1. But we are going to look at a situation where the coefficient is not what? Any of these two values. So now the special situation, that's the 1 minus 1, not special. So I'm going to have d dx of what? 2x plus plus y squared minus what? 3x squared y to the power 4 is equal to d dx, okay, of what I have here, which is minus 8x. Is that clear? Point well made. Okay, so now you are going to differentiate term by term. If you differentiate 2x, what do you get? You get 2. Do you agree? Plus, now you are going to differentiate y with respect to x. The variable that you are differentiating with respect to is not the same as this. So it means you always get a dy dx term. I mean, factor in it after bringing down your power. So you get a reducing your power. So now by 1. So you get 2y, then dy dx. Then this will give you, this is where you have to be very careful. Okay, you have 2 ways of dealing with it. One, you can keep the minus 3, okay, and differentiate the s squared y squared using the product s squared y to the power 4 using the product rule. Okay, and later push the minus 3, okay, inside to multiply all the terms, because once I'm using the product rule, I'm going to get what? 2 terms. Another way is to consider the whole of the minus 3x squared as a factor. And the other factor would be y to the power 4. So let's see the first one. I held the constant. I'm differentiating x squared y to the power 4. So I hold x squared. If I differentiate y to the power 4, I'm going to get what? 4y cubed dy dx. So let me use dot here. Dy dx. Okay, but that's not all. Plus, I come and hold y to the power 4 and differentiate what? My s squared. So it will be dot s squared. Is my point well made, or I should come again?
Please come again.
Okay, all right, I'm going to repeat. Okay, you can see that the 3 here is a factor. Anytime you are differentiating and you have a constant factor, you can always bring that constant factor. Okay, and because your differentiation usually affects variables. So keep your constant factor and come and differentiate your variable or variables here. So I kept my constants. Now I am differentiating the s squared and s to the power 4. So I know I will get 2 terms. So let me use the square bracket. That means I have to hold x squared, then multiply that by the differential of s to the power 4. Remember, I'm supposed to use the product rule. So that will give me the differential of y to the power 4, will give you, you bring the 4 down, keep your y, reduce the exponents by 1. Okay, but that's not all, times what? Dy dx. Is that clear? Okay, this is just about holding the first one and differentiating the second one. So now your second term will be hold the second factor, which is y to the power 4. Differentiate what? The first factor, which is x squared. So that will give you 2x. Do you agree? So now you come and push the negative through. So it will be negative 3 through. So you get negative 3 times this times this. So that will give us negative 12 x squared y cubed dy dx. Then negative what? 6, okay, x y to the power 4. Do you agree? Hello, do you agree?
Yes, please.
Another way is to consider the whole of the negative, okay, 3s squared. As if it was plus, then you consider the 3s squared as a factor, okay, and y squared as a factor. Remember, I've told you, if you have 1,000 factors, you can always treat them as what? As 2 factors. Just as if you have 1,000 terms, you can treat them as 2 terms. So here I have 3 factors, indirectly minus 3, s squared, and s to the power 4. Okay, I'm going to treat this as, so in that case, this is how I will deal with it. I will hold the minus 3s squared. So let me write it this way to be plus. Okay, hold the minus 3s squared. So I'm holding minus 3s squared. Then I'll differentiate the y to the power 4, which gives me, okay, 4y cubed dy dx. But that's not all. Then I will come and hold, okay, the y to the power 4. So plus y to the power 4. And differentiate the minus 3s squared. So that gives me minus 6x. Okay, am I right? Minus 6x. If you differentiate minus 3s squared, you get minus 6x. Is that clear? And that should be equal to, the differential of this will give you minus 8. So in effect, I'm going to get 2 plus 2y dy dx. Okay, then this gives me, if I remove the bracket here, I'm going to get, okay, minus 12 x squared y cubed dy dx. And you can see that it's the same as this. Can you see? When we brought out the negative and considered only the x and the y. Okay, then, okay, that's not all. Minus, this will give you 6xy to the power 4, and it's the same as this. Can you see? And that is equal to, okay, minus 8. So at this point, you collect your terms in dy dx on one side, just factorize. But however, before you do that, check whether you can reduce the equation. And you can see that each term there is a common factor of what? 2. So you can reduce before, okay, making whatever that you want to make the subject, which in this case is dy dx. Point well made. Okay, so I want to see if indeed you really understood how to differentiate a situation where there is a constant. Okay, so maybe minus 2x, okay, to the power 6, then y to the power 5. Okay, someone should differentiate this with respect to x for me. Let me pick the person at random. Okay, as for implicit function, you have to get it. Okay, so let me see. Okay. Okay, so Prof. Daisy, let's go. Let's see how you'll be able to apply what you, just don't be afraid to try. Just try. If you get locked somewhere, we are here to help, we'll help you. And by that, you build your level of understanding. Okay, so let's go. This will be equal to, do it systematically. Prof. Daisy. Prof. Daisy, are you there?
Yes, please.
Let's go.
6 times minus 2.
6 times minus, so you are holding, let us know, what are you doing? Are you holding, which factors are you considering now? You need to have 2 factors, so which one is your first factor?
X.
You are considering only x. How many factors do you see here?
Minus 3 factors.
3 factors, which are?
Minus 2x and y.
Minus 2.
X to the power 6 and y to the power 5.
Because I had x and y. Okay, so now let's go. So how will you group them? So are you going to bring out the negative 2 and differentiate the x to the power 6 and the y to the power 5, or how will you deal with it? Let us know your technique so that we can appreciate.
Yes, I'll bring the negative out and differentiate.
Okay, so your negative 2 will be out. So it means now your factors will be this and this. So let's go.
X to the power 6.
You are holding x to the power 6.
Times 5 to the power.
5 to the power.
No, y to the power 4.
Y to the power 4. You've not brought the exponent down and you are reducing the exponent. Do you get it?
Y.
5y. Bring the exponent down before you can reduce.
To the power 4. Dy dx.
Dy dx. Okay, very good. So far, so good.
Plus y to the power 5.
Plus what? Y to the power 5.
Times 5x to the power 5. Sorry, 6x to the power 5.
6x to the power 5.
Close bracket.
Very good. Okay. Okay, so at this point, if you like, you can simplify this, multiply this, then later you come and push the negative 2 through, or you can combine the 2 at the same time. So I'm going to multiply negative 2 and all this. So that will give us negative 10, okay, x to the power 6, okay, y to the power 4, dy dx. Okay, then this one will give us, this times this will give us negative 2 times 6 will give us negative 12. Then you get s to the power 5, y to the power what, 5. As simple as that, you are done. You get it? So it is easy. Okay, I usually, deal with it the same way as you dealt with it. I always bring the constant out and deal with it this way, and later push the constant through. Okay, but I wanted you to know the other way too, because I've done that one. Okay, all right, so very good, Daisy. All right, only that, make sure, bring the power down before you reduce the exponent. Always, all right. Okay, so on that note, I think we are good to go. Okay, so let's move on to the differential of trig functions. Okay, take note, the basic trig functions, you need to know they are differentials. And the basic trig functions are sine x, cos x, okay, tan x. Okay, tan of the angle x, cos of the angle x, and sine. If you differentiate sine, you should know this. We can prove, but I'm not supposed to take you through the proof. You can prove using limits, okay, and using, okay, the first principle differentiation. Okay, so take note. Anytime you have sine and you differentiate sine, you get cos. If you differentiate cos, you get minus sine. Take note. If I differentiate sine, I get cos. If I differentiate cos, I get minus sine. I don't get sine. Take note of that. Okay. And if you differentiate tan, you get this. Usually, I don't give students this straight away because I know tan can be expressed in terms of, so assuming y is equal to, or I'm differentiating, let me write d dx of what? Of tan x. I know this will be equal to d dx. Once I know how to differentiate sine and cos, I should be able to get the differential of tan because tan is the same as sine x over tan x will be the same as sine x over cos x. All correct. Is that clear? Are you with me?
Yes, please.
Okay, so now my operator is affecting quotient of functions. So I have to use the quotient rule. So this will be equal to quotient rule. What do? I hold my denominator function, which is cos x, then differentiate my numerator function. If I differentiate sine, I get cos. So cos x, then minus, okay, then I swap. This time I will hold the sine function, then differentiate the cos function. And the cos function, if I differentiate cos, I'll get minus sine. Is my point well made?
Yes, please.
Sure. Okay. Then all over. Remember we said your denominator, okay, function squared. Okay, so this will be equal to cos x squared. Cos x times cos x will give you cos squared x. Is that clear? Then plus sine x times sine x will give you sine squared x. All over. Your denominator is also the same as cos squared x. That's how best we can write it. By your numerator, you know sine squared s plus cos squared s, or cos squared s plus sine squared s, we all know is equal to 1. You get it? All over cos squared x. So now what do? We know 1 over cos is the same as what? Sec. So 1 over cos squared will give us what? Sec squared x. So if you are asked to prove this, okay, this is how you prove it. You prove it from the perspective of sine over cos. Point well made. So you just need to know the differential of these two. Basically, you know the rest. Okay, however, we can equally give you. So the basic ones are the one that you should know, okay, directly. And the basic one, we have 3. So you should know that of the cos, that of the sine, and that of what? The tan. Take me with this one too, if you forget, okay, it is in the 4 figure table or your statistical formula book. Okay, so as for these ones, I won't talk much about that because of time. So let's look at how to deal with this. Okay, again, let me look at the solution. Okay, so the differentiation, okay, 1. I. What are we giving? Y is equal to sine what? X plus cos x. So I won't do all of them. So I'm differentiating with respect to x. It means I'm taking d dx of both sides. So d dx of y will be equal to, okay, d dx of what? Sine x plus cos x. Okay, so this will give me, therefore, dy dx will be equal to, my operator is affecting some of functions, so I have to differentiate term by term. So it will be d dx of sine. If I differentiate sine, I will get cos. Then d dx of cos, if I differentiate cos, I will get minus sine. So this becomes the differential. As simple as that. You can't simplify that. So it means with this one too, is the same thing. It will be the differential of 3 sine x. Okay, you can always bring the constant out. So that will give you, okay, 3 cos x here. Then this will be minus sine x. So it will be plus sine x. You get it if you differentiate. Point well made. Okay, so maybe one example maybe will not be enough. Let me do the third one. Okay, what are we giving? Y is equal to 4 sine x, okay, plus 7 cos, okay, x. So I know dy dx are mature, therefore dy dx will be equal to, I'll differentiate term-wise. So I'm going to get 4, I differentiate sine, and that will give me cos x. Okay, then, okay, plus 7, I differentiate cos, and that will give me minus sine x. So in effect, I'm going to get 4 cos x, then minus 7 sine x. All correct. Okay, so this is it for simple, okay, trig functions, okay. And with this one, it is product. So let me quickly chip in that here. If I'm differentiating this dy dx, okay, will be equal to, you treat it as product. So hold your x, differentiate sine, and if I differentiate sine, I will get cos x. Okay, then plus, come and hold the sine x and differentiate the x. If you differentiate x, you get 1. So it means this in effect will give you, okay, x cos x, then plus sine x. Okay, this one too is the same thing. Hold s squared, differentiate sine x. So that will give me s squared cos x, then plus whole sine x, differentiate s squared, and that will give you 2x. So in effect, I'll get s squared cos x, then plus 2x, okay, sine, okay, x. Please don't come and multiply this and this. This is not an angle, it's a coefficient, just that is an angle. So this should always come here when you multiply. Is that clear? Okay, so on that note, is the same thing. Okay, you treat this one as product, this one you treat it. So this will give you x cos x plus sine x times 1. So you get s cos x plus sine x, then minus what? Sine x. Because if I differentiate cos x, I'll get minus sine x. And that will be it. All correct.
Yes,
okay,
please.
so quickly, let's move on to the situation where we have composite, okay, trig function. So this one too, when you are differentiating, you use the quotient rule. Okay, you know. So you hold this one, differentiate this, minus, swap over the denominator squared. Okay, the same thing. You use the quotient rule in differentiating that. Okay, now let's look at a situation where you are dealing with a composite trig function. Okay, the simple trig function, the x, there is nothing multiplying it apart from 1, and there is nothing adding to it apart from 0. So anytime you are having sine of what? Any angle which is in a variable, and the coefficient ceases to be 1, okay, and also what is being added ceases to be 0, then you are dealing with a composite function. So in that case, okay, you need to know how to differentiate composite function. It's the same way, okay, what is making it composite is this, the 2x. So when you do your normal differentiation, you have to multiply it by the differential of what is making it composite. Okay, so now what do I have here? I have a, 4a. Okay, I've been given y is equal to sine 2 what x. So now my dy dx will be equal to d dx of what? Of sine 2x. Okay, here, remember, it is a simple one when the coefficient here is 1 of your x is 1, but it's not 1, and the constant of the being added is 0. So it's composite, and whenever you are factorizing composite trig function, this is all that you need to do. So if I have, okay, sine, let me write sine, okay, f of x in general, okay, this will be d dx, okay, of sine f of x will be equal to, I will deal with it as if I'm doing normal differentiation of sine. So that will give me cos my f of x, but that's not all, times the differential of what? The f of x. The same thing for the composite function. So it will always be, you can see that the other one, because the coefficient is 1, okay, if you multiply by times d dx of x, it will give you 1. So you usually don't consider it. This factor will always be 1. So when you differentiate the function straight away, you land at the answer. But with this one, no, the coefficient of the differential of the function, making it composite, will not be 1. So it means this will be equal to deal with it as if you are doing normal differentiation of, okay, three functions. So this will give you cos 2x. But that's not all. Then times the differential of the function that is making it composite, which is the 2x. So differential of 2x will give you 2. So in effect, you are going to get 2 cos 2x. Is that clear?
Mr. Akman, please come again.
Okay, I'm going to come again. I think no problem at all. So let me clear this. And maybe this being the first one, let me go through. So composite function, you know, when we're dealing with a composite function where, okay, we have, okay, f of x to any power, we use the normal differentiation rule. Bring the power down, keep your function, reduce the power, okay, then what? You multiply by the differential of this. The same way, composite in terms of a trig, you deal with this as if you are doing your normal differentiation. So you differentiate what? Okay, the sign here, which will give you the cos 2x. Okay, but that is not all. It will be times the differential of the function that is making it composite. And that will be 2x. So with this one too, you know that it will be n down, f of x. You reduce the exponent by 1, but that's not all, times the differential of the function that is making it composite. Okay, so that would be your differential of f of x, g dx of f of x, which will give you f prime of x. So here, I think now it's better. I know this will give me cos 2x, then times the differential of this will give me 2. And remember, this is a coefficient, this is an angle, this not. So this then gives you, okay, I'll write therefore here. This then gives you 2 cos 2x. So it means, again, if I have, okay, let me look at the B. Okay, if I have y is equal to cos 3x, okay, what I'm taking cos of is not a simple function, it's not x. It is 3x, even if it was x plus 1, you can see that though the coefficient of x is 1, what is being added is not 0. So it's still a composite word function. So if it is this way, cos, okay, x plus 1, then this one you treat this as terms. Cos x and 1 will be 10. But if it's cos x plus 1 with the x plus 1 in bracket, then it means this is your function f of x, which ceases to be what? X. So in that case, it ceases to be, what do you call it? A simple one. So therefore, if I differentiate this with respect to x, I deal with it as if I'm doing my normal differentiation. If you don't know this, and I ask you to differentiate this, okay, you don't know the composite, you are not able to recognize this as composite. What will you write? Wouldn't you write minus sine 3x? I guess that's what all of you will write. Is that not it? Because you know the differential of course is minus sine. So you all write minus sine 3x. But unfortunately, that's not all. Okay, if you are not able to see this as composite, then you know that factor, you will not consider it, and therefore you will get it wrong. So it will be times the differential of the function here. You know, you take trig of functions, so sine, okay, so we are going to get the differential of what? So d dx of 3x, but as you mature, you can do it mentally. So that gives you minus sine 3x, then times what? D dx of 3x will give me 3. So I will get minus 3 sine 3x. I'm done. Is that clear? So if you look at this carefully, this will also give you, if you differentiate tan, you get sec squared. So it's going to give you sec squared for x. Okay, but that's not all. Times the differential of 4x, that will give you 4. So it will give you 4 sec squared for x. That's your final answer. Is my point well made? Hello, Fedaios, is my point well made now? For Fedaios. Point well made. Okay, now let's look at this situation, which will be the last one. So if I have, it's the same technique. D, y is equal to sine 2x plus 1. Okay, because of this, it is no longer simple. So I have to make sure after doing my normal differentiation, I have to multiply by the differential of what? The function that is making it composite. And you are good to go. So what do we have? we are going to have, therefore, dy dx, okay, will be equal to, okay, if you differentiate sine, you get cos. Then your angle is kept 2x plus 1. But that's not all, times d dx of what? The angle. Okay, your function 2x plus 1. So this in effect will give you, okay, cos, okay, 2x plus 1 in brackets. Okay, then times, okay, your 2x plus 1 differential will give you 2. So I will get 2 cos, okay, 2x plus 1. Afa, is it clear? Is my point well made?
Yes, please.
Okay, so take note. And this one, you treat it as sum. So the differential of this, okay, times d dx of this, but this is a composite function. So when you are differentiating this, you have to use the composite function technique, which will give you minus 2 sine 2x. Okay, you should know that. All right, so I think that will be it for that. Now, when we talk of the higher derivative, we are going to look at what? Further derivatives. So we know how to differentiate, okay, the first time, what we call the first derivative. Okay, now you can, every function, okay, you can differentiate likely more than once. Okay, only at a point, okay, when you differentiate, you always get 0. Okay, so this is it. Anytime in calculus, okay, if you find d dx of y, we know this is equal to what? Dy dx. Is that not it? That's the notation. Is that clear? Now, this dy dx, you can differentiate again. So if I'm going to differentiate, so if I find d dx of this function d dx of y, this will be equal to d dx, okay, of my resultant function here, which is dy dx. And this is how we write this notation. If you differentiate twice, okay, this becomes d squared y over, in actual fact, usually you might think it will be dx all squared, but that is not it. Okay, it will give you d squared what? X. Hello, are you with me? Yes, Kobe.
I thought it would be d square y d x
S
square.
squared,
Not
very good. Okay, so very good. All right, so this is it. The power of your x will tell you the number of times you are differentiating that, okay, variable with respect to. Okay, so this is not the notation. The notation, anytime you have d dx, okay, of dy dx, okay, this gives you d squared y over ds squared. So the power of the x here will always tell you the number of times you are differentiating, okay, your variable that your function contains with respect to. So in the same way, if I have d dx of my second derivative function, dy ds squared, okay, this will give me d cube y over ds cube. So in general, I will have d n, okay, y over dx to the power n. So the n will tell you the number of times that you are differentiating with respect to, as simple as that. Okay, so if you're able to differentiate a function once, you should know how to differentiate it twice and what have you, as simple as that. So please take note, this is not the notation, and equally, it is not, okay, d squared y over dx, okay, all squared. It is not these two, any of them. It is rather, the notation is this one. So take note. Now let's go and apply that, okay, to the questions that we have here. If you get the first derivative, it's a second derivative, I'm okay. Because usually we don't go beyond the second. Okay, so we are going to get, okay, solution to question 1, okay, A. Okay, what are we given? Y is equal to x to the power 4, okay, plus 2x cubes, 2x cubed, okay, minus 3x squared plus 1. Okay, so your first derivative, you are asked to find dy dx and what d squared y. So therefore, dy dx, okay, I will differentiate straight away. So that gives me 4x cubed plus 6x squared minus 6x, then plus what, 0. You don't write. Is that clear? So that's your first derivative. If you are not able to get your first derivative right, your second derivative will be wrong because you rely on your first derivative function. Okay, so even this question, I could have, asked you to find d squared y dx squared straight away. But either way, you have to go through what's the dy dx, the first derivative. So on that note, and therefore this is equal to that, and d squared y over dx squared, will be equal to, now you are going to differentiate this function again. So that will give you 12x squared plus what, 12x minus 6. As simple as that. So you differentiate, if you are asked to find the d cube y over ds cube, then that will give us 24x, plus what, 12. If you differentiate again, s to the power 4, what have you, you end up getting 12. So any function you can differentiate as far as to the power to the power of your highest variable, the highest degree of your function. After that, any other derivative will give you 0. So if I ask you to find the to the power 5y over the s to the power 5, you will get 0 because I've gone beyond the power, of what, the highest power of what. So if you end at the highest power, you always get the coefficient of this. So here, I'm talking about you get a constant. Let me put it that way before I make this error. You get a constant. If you differentiate up to the power, the power will end up giving you a constant. After the constant, you get 0. Any other differential will give you 0. So it's the same thing. So with this one, let me come to this. So this, yb, you know that we are going to have y to the power 1 over x. The exponent must be explicit. Otherwise, you use, the quotient rule that we can avoid. So that will give us s to the power negative 1. So it means my dy dx, therefore, will be equal to, bring the exponent down, x to the power negative 2. You can choose not to write a 1 there. Which in effect, the function didn't come with a negative exponent. So I will get negative 1 over x squared. Take note. And your second derivative, when you come back to this, so you use this one instead. So and my d squared y over ds squared, will be equal to, this time right, minus s to the power negative 2. So the negative 2 will come down and multiply. I will get a positive 2, then s to the power negative 3. I'll reduce the exponent by 1. I cannot conclude with negative because my function didn't come in negative. So I bring, the power down. X and the power becomes positive. Is my point well made? So with this one, unfortunately, you cannot avoid the quotient rule. So your first derivative, you use the quotient rule. Your second derivative, you use the quotient rule. Please take notes. All right. So that will be it for what we have there. Is my point well made? All right, so I think with this you should know. This one, I can avoid, the quotient rule as well. Only that if I want to avoid the quotient rule, then I have to use the power rule. So in that case, this is what is going to happen. So D, I will write y is equal to x plus 1 to the power negative 1. So I will use the power rule. I usually call the general power rule, which is the composite one. So my first derivative will be dy dx. Will be equal to, I bring the exponent down, minus 1 down, keep my x plus 1, reduce the exponent by 1. So minus 2, but that's not all, times the derivative of this, which is 1. So in effect, I'm going to get what? Minus, into x plus 1, to the power negative 2. So that gives me minus 1 over x plus 1 squared. Because what the function came with, there was no negative exponent. So if I want to differentiate again, then I have to use this one. So if I'm differentiating again, I'll bring the negative 2 down, which will make it positive. So indirectly, I'm going to get, let me see whether I created another page. Yes, I did. So, and my d squared y over ds squared will be equal to, remember, there is a negative up there, -2. It will come and multiply the -1. So you get +2. Then you get x, okay, plus 1. All to the power, the -2, you reduce the exponent by 1. So it's -2 minus 1. So that gives you -3. Okay, but that's not all, times the differential of what you have in bracket, but that will again give you 1. So in effect, we are going to end up getting the second derivative also to be what? 2 into s plus 1, the power -3. You bring the power down, so you get 2 over x plus 1 all cubed. Is my point well made? Okay, so that will be it for what we have there. Okay, now let's look at another way. If you're able to solve the first question, I will guide you to solve the second question. Okay, that will serve as a guide. Okay, there is another way, but use the first approach if possible. Okay, so this is what we have. Okay, we are going to look at what the first question together. An interesting question. Find dy dx, then d squared y ds squared, then show by direct substitution that this. So when you read the question, you know, I've told you immediately you see show. Okay, you have to underline. Show, very critical. It will guide you as to how best to draw your conclusion. So question 2a. Okay, what am I giving? I've been giving y is equal to 1 over 2 minus x. Let's see what is going to happen. Okay, now I need to find dy dx, and so I have two questions in one here. The first part of the question is 2 in 1. So I have to draw two conclusions. Okay, one for dy dx and one for d squared y over ds squared, because it's a direct question. So now I will say that in this case, I want to avoid the quotient rule. If you want to use the quotient rule, you can, but I want to avoid. So I will use the power rule, okay, or the composite function. So I'll write this one as, just as I did for the other one, 2 minus x or to the power -1. Do you agree? Okay, after that, we'll handle it from the composite, sorry, the chain or quotient rule perspective. So in this case, my dy dx will be equal to, I'm differentiating this, bring the power down, 1 is simply understood to be there. This time I won't write it. Okay, keep your 2 minus x, reduce the exponent by 1, so that will give you -2. Then times the differential of what you have in bracket, and this will give you -1. Is that clear? Okay, so in effect, we are going to get the negative and the negative will multiply. So I will get positive, okay, 2 minus x all to the power -2. Okay, which indirectly, okay, is the same as what? 1 over, okay, 2 minus x all squared, oops. All correct. And your second derivative, you work on this. So d squared y over ds squared will be equal to, bring the exponent down, so -2 will come down. Keep the 2 minus x, reduce the exponent by 1, so -3. Then that's not all. This will also be times -1, the differential of the function that you have in bracket. So in effect, we are going to get, this will give you +2, then you get your 2 minus x to the power -3, which gives you 2 over 2 minus x all cubed. All correct. So the first part of the question dealt with, is that not it? Hello, is that not it?
Yes, please.
Now let's go and look at the second part of the question. So the second part of the question, what are we giving? What are we asked to show? That y d squared y over dx squared is equal to 2 d squared y over ds, sorry, dy dx all squared, forgive me. So there is it. Anytime you want to prove, okay, we have two ways. Take the left-hand side, compute it, take the right-hand side, compute and compare your results. Or take the left-hand side, okay, compute it and transform it to be the same as what the right-hand side. So by that, that's what I'm going to do. All right, taking my left-hand side, which is y d squared y over x squared. Okay, and this will be equal to, so y, what is y? Y is 1 over 2 minus x. Okay, then times your d squared y over dx squared. What is d squared y over dx squared? Which is this? Is that clear? So that will give you times 2 over what? 2 minus x, because here we were asked to use direct substitution. So that will give us what we have here. So in effect, I'm going to get 2, this and this will multiply over this and this will also multiply. So I'll get 2 minus x to the power 4. Do you agree? Do you agree? Hello, do you agree?
Yes, sir.
Okay, but you can see that if you like, you can hold on here, go and take the other one too. Okay, and simplify. But I want to manipulate. I want to work with one side to get the other side. So I know that this is equal to 2, okay, times what? 1 over, okay, looking at the form, 1 over 2 minus x all to the power 4. Do you agree? So what I have here is the same as what? 2 minus x, okay, 1 over 2 minus x, the whole of that squared. So I'm going to continue to the next page and let's see, okay, let me assume this is my next page. So if I continue, I'm going to get this to be equal to 2, okay, times what? 1 over 2 minus x, okay, squared, all squared. Can you see that? Do you have that, eyes? So 1 squared will give you 1. This 1 squared will give you x to the power 4. But you know that this is equal to 2. 1 over this is dy dx. So I will have dy dx, okay, squared. So therefore, okay, this is equal to that as required. Is my point well made? Or like I said, okay, just come and take this side too and work with it and see whether you end up getting exactly what is here. So let me equally do that. So so you are done with the other side. So taking 2 d squared y over dx squared, dx all squared. So this will be equal to 2 times what? D y dx all squared. Dy dx give us 1 over 2 x minus what? Minus, it's 2 minus x, not 2x. 2 minus x all squared. All squared. Okay, that is your y, but it's the whole of this one. Well, that's your dy dx. So the whole of this one squared. So dy dx, I substituted, and this is what we had. Okay, 1 over this. So I'm right, 2 minus x, okay, all squared. So now this is what we have. So if I continue, I'm going to keep my 2, which will be 1 squared, which is 1, over 2 minus x squared squared, and that will give me 2 minus x all to the power 4. So in effect, I'm going to get 2 over 2 minus x all to the power 4. And obviously, you can see that the two results are the same. So I can draw my conclusion as such. You get it? So with that approach, you end here for the first one. Okay, then you come and work on the other side and you end here. And you can use the same approach to deal with this. Okay, there is another approach, but use the direct substitution. So meaning you have to find dy dx, you have to find d squared y over dx squared. Take the left-hand side. Usually go for the side that you have more materials. Anytime there is a show question. So go for this side, substitute and manipulate to get this. Okay, when you substitute your d squared y over dx squared, even this y doesn't involve fraction, so you can easily get it. So you are going to get y is equal to 3x squared minus x. So it means your dy, okay, ds, here you were asked to show, but you want to use the direct substitution, so you don't draw your conclusion for this, because you were not asked directly to find dy dx. So dy dx, you will need it, is equal to 6x, okay, minus 1. So the square, d squared y over dx squared, will be equal to what? Okay, 6. Is that clear? So in that case, I can say that by then I know this taking the left-hand side, taking, okay, y, d squared y over ds squared, okay, plus dy dx, okay, minus 6y plus 1. That's, I'm taking the left-hand side. This will be equal to y. What is your y? I even know my y, which is this. So let me substitute everything that I know there. I can, once I know y, any direct substitution should go for what I have there. So y is what? 3x squared minus x in brackets times d squared y, okay, and that gave us 6. D squared y over ds squared, that is 6. Okay, then plus dy ds, ds give us 6x minus 1, then minus 6y, then plus 1. Oh, sorry, we know y, sorry, forgive me. So let me equally go and substitute y. Okay, so I will get y, which is what? Y give us what? Y is, we do 3s squared minus what? X, but that's not all, plus 1. Okay, so this gives us what? Obviously, you can see this quantity here. So this will cancel this. You can see this minus 1 plus 1. So we end up getting 6x, which is the same as what we have on the side. So therefore, what you have here is equal to this 6x as required. Having underlined the show. Is my point well made? I know I moved a little fast, but I believe you are able to relate. Just find your first derivative, your second derivative function, then come and substitute your y. Okay, you can see y there. Substitute your y, substitute your dy dx, and substitute all your known parameters after finding them. Okay, and you are good to do. So you do same for all that you have here. As simple as that. Is my point well made? Okay, so quickly, let me take you through the application we are done. Okay, when you get, the first application will be gradients. Okay, so please, let me ask you, if you have, I think, let me go to the solution. If you have, okay, y is equal to a linear equation 2s plus 1, what is the gradient of this function, this line? What is the gradient? The gradient is 2. Is that not it? ms plus c, the coefficient of s becomes your gradient. Very good. Now find dy ds for me. Dy ds will give you 2. So you should know that, okay, by this, anytime you have a function, immediately you differentiate once. The first derivative will give you the gradient function. If it is a line, the first derivative will give you the gradient straight away. But if it is any curve, any function more than the degree 1, okay, if you differentiate, you are going to get, okay, your differential function, which is your gradient function, to be in terms of x. So your first derivative will give you the general gradient. However, if you want to get a particular gradient, because I'm dealing with a curve, okay, for lines, irrespective of where you are on the line, the gradients will be the same. But for curves, if I have a curve, if I'm here, my gradient will be different from, okay, someone who is here, someone who is here. So the gradient will differ from one point on the curve to another. But if I have a line, anywhere am I on the line, the gradient will be the same. Do you agree? So anytime you are asked to find the gradient of any function, just differentiate the function. But we will ask you to find the gradient at a point so that you all get what the exact gradient that we are looking for. So in this case, this is what you do. I will do only one, and as a guide, you use it to do the rest, and that will be it. So I've been given y is equal to 1 over 3 s cubed, okay, minus s squared minus 24x plus 5. And I'm finding the gradient at what? The point 0, 0. So I've been given this and that. Okay, so I know that gradient, okay, maybe m is equal to your dy dx of this function evaluated as the x value. okay, of the x coordinate. So that will give you x is equal to 0. Or you can ignore this, okay, and just write is equal to dy dx. Okay, let me put it this way. Instead of, this is the matured way of writing it, but there is another way. Okay, so with another way of making this same statement. So I write it will be dy dx at x is equal to 0. So in this case, I'm going to get dy dx will be equal to, let's differentiate this. This gives us x squared. The 3 will come down, it will cancel. Minus 2x, then minus 24. Is that clear? So this is the general gradient function. So if I want to get a particular gradient, I have to know the exact value of x. So now at x is equal to 0, my dy dx, which is the gradient, I'll conclude with the gradient, will be equal to 0 squared minus 2 into 0, then minus 24. So therefore, my gradient, okay, will be equal to minus 24. Point well made, or I should come again? Point well, I should come again. So here, you can see it's an application of differentiation. I remember I told you, if you don't know how to differentiate, even if I take you through the what do you call the concept of the application, you wouldn't be able to deal with it because your differentiation must be strong. So I'm saying that anytime you differentiate any function, okay, you get the gradient function. The gradient function could be a constant function if you are dealing with a line, or it could be a variable function, as you saw in this case. We are dealing with what a cubic function. So anytime you differentiate your function, you get a gradient function. So if you are looking for a particular gradient, because the gradient function will depend on x. If your function depends on only x, your gradient function will depend on x. Therefore, if I want to get a particular function, I have to substitute a value for x at that point. So we'll give you the points. Okay, so that you all have the same gradient because we are located at the same point on the curve. And that point, you only need the x coordinate and you substitute. However, okay, let's look at this implicit function and see, okay, whether we need only the x or y. So far, if you have considered what we've done so far, so d, okay, y is equal to, sorry, I'm doing e rather. Okay, e, let me cancel e. What am I giving? I've been giving x squared plus y, okay, squared is equal to 5. And at which point? At, okay, you can ignore the at and even write 1, 1, 3. Okay, your point. Okay, now we need to find dy dx before we can substitute. But this is an implicit function. And for implicit function, if I want to find dy dx, I have to apply my differential function, take d dx on both sides. Remember where we are coming from. Is that clear? So this gives you 2x plus, now we are mature, 2y dy dx is equal to 0. So we are going to get what? I can divide through straight away. So I'll divide through by 2, and that gives me x plus y, okay, dy dx. Then now I'm going to get, okay, or you can then later divide, which is what we did in the first example. That's the more reason I'm giving you this alternative. So it's equal to 0. So I will get what? My y dy dx will be equal to what? Minus x. So I will write it again and divide. So therefore I will get, I'm not asked to find, okay, the dy dx. I'm asked to find the gradient, so I cannot write therefore. So I'll write dy dx will be equal to minus x over y. So you can see that because my function is implicit, okay, my resultant, okay, depended, or I mean my function, which is the first derivative function, therefore my gradient function, okay, it is dependent on both x and y. So this time around, you have to substitute your s value and what? Your y's value here, your s coordinate and the y coordinate. So I will say that, therefore, my gradient, okay, will be equal to, remember we said the gradient will be equal to dy ds. So at that point, will be equal to, so at which point we know, okay, x is equal to 1. So it will be minus 1 over y is equal to 3. So this then becomes the gradient. So with this one too, you define your dy dx in this implicit function, which is likely to be in terms of x and y. Then you substitute the x and y values here, and that will give you the gradients adapt. Afa. Is my point well made? Okay, so if that's the case, we are going to end here. Okay, very good. So take notes. Okay, and once you are able to find the gradient, you could be asked to find the equation as well. So I can ask you to find the equation of a line, okay, at the point, meeting the curve at this point. Okay, once you have this concept, please go and read. You get the rest. Okay, you get the rest. The rest you can relate. The purposely, you need to know how to differentiate, and now we know how to differentiate all, okay, functions, irrespective of their nature. Okay, so differentiation is clear. God willing, okay, tomorrow, which will be our last meeting, we'll look at integration. Okay, then, I mean, how to integrate. As for the application, okay, when you go back to school, you can read, or when your teachers teach you, you know how to differentiate. So get the steps in, okay, dealing with what? That approach in terms of the application. Then you are good to go. Okay, so thank you very much. I think I've exceeded, okay, but the purpose was to end here, and it ended here. Okay, and this one, quickly, find the grade at the point where the curve cuts the y-axis. So with this one, you can see that the point is not given directly. Okay, so with the gradients, this function will depend on the grade dy dx will be 2x plus 6. It's dependent on x, so I need to know the x that I can substitute. And how do I get the s? We are said at the point where the curve cuts the y-axis. So you have to write at the y-axis, okay, s is equal to 0. So you substitute the x being equal to 0. Okay, you get it? Is my point well made? Okay,
Yes,
remember we agreed that, okay, tomorrow class will end, okay, in the morning. We'll have an evening class, unless maybe there is a special situation. Otherwise, that was the agreement initially. You said we should end on, you even wanted us to end on Monday. And I said, let's meet on Tuesday, okay, and I mean in the morning, so that you can have a little time to prepare and can go back to school. So let me explain this. You need your s here. X is not also given. The s that, so he said, cut the x-axis. Determine, so at the point where it cuts the x-axis, you know, okay, at the x-axis, y is equal to 0. So you substitute y is equal to 0 here. You solve this, you get 2 x-intercepts, 2 s values. Then you are asked to find the gradient, okay, at these points. So you take the first point, you put the s coordinate into your dy ds, which is 2x minus 1. So your first x coordinate, you put it there on the first point, and that will give you the gradient of the curve at that point. And your second s coordinate, you put it into your dy ds function, and that will give you the gradient of the curve at that particular point too. As simple as that. Okay, so this is where I ended. Thank you very much. God bless us all. Okay, make sure you practice. I ask you to remind me to send you, okay, some videos. I mean, some, what do you call it? Okay, so God bless us all. Let me stop it.